Welcome to Essential Problems with CRIP. This video will focus on applying periodic trends in order to solve a particular change in energy for a given process. So let's begin. You will need to have this handy reference sheet for our elements, including the several first, second, third, fourth, fifth, sixth ionization energies, as well as several electron affinities for these elements. So let's begin. We're going to begin with a sample problem here involving lithium, an atom of lithium gas, reacting with an atom of fluorine gas to produce a lithium ion, lithium positively charged, and fluoride ion negatively charged. And we're going to solve this in change in energy per mole, because all of these provided values are in kilojoules per moles of reaction. So in order to do this properly, what you should always do is break up the reactions that's provided. And so we're going to begin with lithium and forming lithium positive with a positive charge. By writing this down, the first step that you should do is to complete the equation by placing an electron either on the product side or on the reactant side. It's the most simplest thing to do, and that's going to indicate what type of process you have. If an electron is on the reactant side, if you had an electron on the reactant side, well, that's going to be a process in which you're binding an electron. It's going to be a process that's associated with electron affinity. Versus if we are putting an electron on the product side, it's going to be a process associated with ionizing that electron, ionization energy. So in this case, in order for us to have a neutral charge, we're going to need to put the electron on this side. And so this is the complete equation, and this is obviously associated with the ionization energy for lithium. In particular, we are focusing on the first ionization energy because it's the first electron that's being ionized. And if I look at my reference sheet, under the first ionization energy for lithium, I have 520 kilojoules per mole required. And so, again, since we are breaking a bond, that's always going to be a positive value associated with ionization energy. So next we go to our next half reaction, in which we begin with fluorine and we're going to end up with fluoride ion. In order to complete this equation, we're going to need to put the electron on the reactant side. And so we can clearly see that we are adding an electron, we're binding an electron to fluorine, and so this is going to be associated with electron affinity, specifically the first electron affinity, because we are adding the first electron to fluorine. And if we look at our table of values under fluorine right here, here's electron affinity. Now, it's important to note that since electron affinity, right, is energy associated with binding an electron, this energy is always negative, meaning whatever value is reported, we need to put a negative sign in front of it. So here we have negative 328 kilojoules per mole. Again, the values here are being reported in just this kind of absolute term of electron affinity in order for us to compare affinities. But that's energy released. So that means these negative values here for electron affinity will become positive, actually, when we apply the negative sign to them. So that shows how low their affinity is, actually would require energy to force them on the atom. So here now we have both values listed, and you can see that if we add both half equations together, we can get our final equation, and that will provide us with our change in energy for this given process, positive 192 kilojoules per mole. We can see how this might change if we just change the type of ions. So if I compare this new problem now, right, to this previous problem, notice how this lithium ion was positive and this fluoride ion negative. You probably are very comfortable with that because you probably already encountered these. The most naturally occurring ions are Li plus and F minus. But what if we had a situation where we formed Li minus or an F plus? So this is not impossible. Um, Anything is possible, and we can calculate the change in energy for this process. So again, we would begin with our little half reactions. So lithium to Li minus. Of course, in this case, we would need to add an electron on the reactant side. So notice how that differs from the previous example in which we placed the electron on the product side. Here we have to place the electron on the reactant side. So this is going to be associated with the electron affinity for lithium, specifically the first electron affinity for lithium. So if we look at our table, here's lithium, and the first electron affinity is 60, so that's going to be negative 60 kilojoules per mole. Here we can bring in our part of our half reaction for fluorine. In order to complete this equation, we're going to have the electron on the product side. And we can see that we are breaking that electron free. And so this will be associated with the ionization energy for fluorine, specifically the first ionization energy for fluorine. And if we look at our table, here's fluorine, and here's our first ionization energy. So that's the energy required to break that bond, and so positive 1681 kilojoules per mole. Of course, if we add these two half reactions together, we can get our change in energy for that process, and that's positive 1621 kilojoules per mole. So notice how this process compares to the previous process. So if we put them side by side, notice this is producing the ions that you're most familiar with, right? That lithium typically forms Li plus, and fluoride, when it becomes an ion, typically forms F minus. Again, that is very much what we experience in nature, but we could, under laboratory conditions, force or create a situation where we have Li minus or F plus. But the key thing here in this kind of simple calculation is to see how radically different the change in energy. It is much easier to do this process than it is to do this process. This process requires substantially more energy in order to occur. Let's take another example. Here we have magnesium plus 2 fluorine to yield magnesium 2 plus and 2 fluoride ions. So we're going to calculate the change in energy for this process. Now you might want to, you might be inclined to want to go from magnesium to magnesium 2 plus directly, but you cannot. It is very important to note that we can only do one step at a time. So magnesium will form magnesium plus first. And if we write this little half equation, we'll realize that we'll need an electron on this side in order for it to be balanced, the charge to be balanced. And that will be associated with the first ionization energy for magnesium. And looking at our table, for magnesium, 738 is the first ionization energy for magnesium. And then we'd have to go on to the second step, which would begin with magnesium plus to yield magnesium 2 plus. And again, we'd have to complete this equation, which would require an electron on the product side. But this is not the first ionization energy for magnesium. We're removing the second electron. Therefore, this is the second ionization energy associated with magnesium. And if we're looking at our table, that's 1451 kilojoules per mole to remove that second electron. Again, that's going to be more difficult to remove because it has a greater attraction to that remaining 1 plus ion. Next, we can move on to the 2 fluorine yielding 2 fluoride ions. Now, in order to complete this equation, we're going to need 2 negative charges on the reactant side, so 2 electrons are required. Now, this is different from this previous example because this is still the first electron affinity for fluorine, right? Electron affinity because we're adding electrons, but we have twice the number of reactions, or in this case, twice the number of moles of reactions. So this will be 2 times the electron affinity, the first electron affinity for fluorine. So we have the electron affinity for fluorine, but that means then we're going to have to multiply that by 2. Of course, it's negative because we're adding that electron, and all of those electron affinity values, when we do the math, we will need to apply a negative sign to them. So now once we have all of these together, we can add these equations up together and we can get our change in energy for the entire process. So let's continue to the next one now. And now we're going to take an outrageous example. So here I have a carbon 5+ ion being added to a nitrogen 4+ ion to yield a nitrogen 5+ ion and a carbon 4+ ion. A ridiculous scenario, but the point here is that if we work carefully and systematically using the same kind of techniques that we just did, you're going to see that this is going to be radically easy. So again, we begin with our simple half reactions. We'll do carbon 5+ to carbon 4+. And again, if you, maybe sometimes students place the electron on the wrong side, but you should always then just do a simple check. It's very easy. So if you placed an electron in this side, that's a negative charge being added to 4+. That would be 3+, and 3+ does not equal 5+. The whole point is that both the total charges on both sides of the equation must be the same. So the only way for them to be the same is to add the negative charge on this side. So an electron must be added here. So notice this, you could say this is electron affinity, but the truth is that we don't have any values of electron affinity for positively charged ions. So we're kind of stuck here. But one thing that we could realize is actually looking at the reverse process. If we look at the reverse process, going from carbon 4+ to carbon 5+, and in which we would have to emit an electron, that would be the 5th ionization energy for carbon. If the reverse process would be the 5th ionization energy for carbon. So we could actually use that. Of course, the way they're related is that this process, as written, would be the reverse of the 5th ionization energy. So in order to use that value, we just recognize that the reverse of that would be negative of the 5th ionization energy. And so if we look up the 5th ionization energy for carbon, so 1, 2, 3, 4, 5, here we have the 5th ionization energy for carbon. We can bring that value, and here's negative 37,831 kilojoules per mole. We can continue on with nitrogen 4+ to nitrogen 5+. Again, we need to complete the balance the equation first, right? In this case, we're really balancing the charges with an electron or electrons. And so electron would have to be placed on the product side. And we can see in this case, it's clearly easy to see that we're going from nitrogen 4+ to nitrogen 5+. So this is the 5th ionization energy associated with nitrogen. And so we can simply look up that value for nitrogen, 1, 2, 3, 4, 5, and that's 9,445. And so that's, of course, a positive value because, as it's written, we're breaking that bond. And so now we're ready to add both equations together. If we bring these together, we get a change in energy of negative 28,386 kilojoules per mole. And we could rationalize why this is such an enormously negative value. Well, we can see that actually for carbon, right, the reason why this value, the 5th ionization energy, is so much larger is because carbon has 4 valence electrons. And so that means that this electron is being drawn from a lower energy level. And so that means then the reverse process, if this electron is being gained again, would be extremely exothermic, versus nitrogen only has 5 valence electrons. We haven't really touched this other electron that's coming from a lower energy level. We could also list more ionization energies, but I have only provided up to the sixth. So technically, there should be also a seventh electron that's possible to list for nitrogen, because of course nitrogen has a total of 7. Finally, we end this video with one of the most common errors that students make, and that's really the conception that everything that we're doing in this unit is revolving around the actual values rather than the setup of the equations. Notice how I have taken all of the possible permutations for ionization energy and electron affinity in reference to one element. Here, notice how aluminum to become aluminum 1 plus and removing an electron is associated with the first ionization energy. To remove the second electron is the second ionization energy. To remove the third electron, third ionization energy. To remove the fourth, fourth ionization energy. To remove the fifth, fifth ionization energy. To remove the sixth, sixth ionization energy. The problem is, what if we were to add an electron to aluminum 6 plus ion? Well, this would be the reverse equation from this equation. This would not be electron affinity. This is one of the most common errors that students make. This is the reverse process of ionization energy 6. So this would have to be negative 6th ionization energy. For adding an electron to aluminum 5 plus, would be negative 5th ionization energy. For adding an electron to aluminum 4 plus, negative 4th ionization energy. To adding an electron to aluminum 3 plus, negative 3rd ionization energy. To add an electron to aluminum 2 plus, negative 2nd ionization energy. And to add an electron to aluminum 1 plus, negative 1st ionization energy. Notice how this radically differs from electron affinity. If you will, ionization energy focuses on positively charged ions versus negatively charged ions is the domain of electron affinity. Here, to add the first electron affinity. To add the second electron affinity. To add the third electron affinity. To add the fourth electron affinity. To add the fifth electron affinity. To add the sixth electron affinity. And to remove that first electron from aluminum 6 minus, that would be the reverse process of 6th electron affinity. And to remove the next electron, and so on. This is very important to note, perhaps the most challenging part of this calculation in this unit. Till next time,